Welcome to lecture number 3, representation of transmission losses using loss coefficients and penalty factor. In the previous lecture, we have discussed about the simple model of a facile plant, and we have seen what are the various curves with respect to cost function. And we also discussed about equality constants and inequality constants. And then we discussed about Lagrange multiplier method by considering both equality and also inequality constant. In this lecture, we mainly focus on how the transmission losses can be represented by using loss coefficients. The loss coefficients can also be called as B coefficients. So generally, the transmission loss is a function of generator powers and is expressed using the loss coefficients or B coefficients. In general, the transmission loss can be expressed by using equation 1.29 here. Here you can see the transmission power loss PL is expressed as summation I is equal to 1 to M, summation J is equal to 1 to M, Pi Bij into Pj, where Pi and Pj are the real power injections at I and j buses, and Bij is called loss coefficients, which are constants under certain assumed operating conditions, where M represents number of generator buses. Suppose if power generation PGs are expressed in megawatt, then the loss coefficient Bij is nothing but reciprocal of that power. So that's why the loss coefficients can be expressed in megawatt inverse. Or in general, you can also call this as per megawatt. This is also called as per megawatt. So here, some of the important conclusion points we can see. So basically, the loss coefficients Bij is also equal to Bji. So that means, suppose if you represent B12, so that is called the loss coefficient between the bus 1 and 2 is also similar to the loss coefficient from 2 to 1 bus. So it is just similar to how from one point to another point, whatever may be the distance is there, if you measure from either sides, it will be same. In a similar way, the loss coefficients are also same if you consider from any bus. It may be from bus 1 or it may be from bus 2. The transmission loss can also be expressed in the matrix form. So here you can see PL, transmission power loss, is equal to power transpose into B into P. So where P is called power and T represent transpose and B is loss coefficient matrix and then P is again power. So the loss coefficients for an n generator system. If any system is having n number of generators, then the loss coefficients matrix will have n by n size or n into n size. And basically the loss coefficient is a symmetric matrix. And here you can see the loss coefficient Bij is represented in matrix form. So the first element represents B11. It is the loss coefficient with respect to bus 1 itself. It is the self loss coefficient. And then the element which is represented here in the first row and second column is B12. So it represents the loss coefficient between bus 1 and bus 2. And similarly, and so on, B1j represent the loss coefficient between bus 1 and bus j. So and so on. Similarly, you can represent all the elements in this loss coefficient matrix. So some of the important observation we can have here. So basically here, this matrix is a square matrix. The first observation is it is a square matrix. And the second observation is the loss coefficient matrix is a symmetric matrix. It is basically a symmetric matrix. So symmetric matrix means, suppose the matrix, if it is represented with B, so B is also equal to B transpose. So then that such matrix is called as symmetric matrix. And here the diagonal elements B11, the next observation is the diagonal elements B11, comma B22, and so on up to Bjj. So all these diagonal elements are positive in nature and are very much strong compared to the off diagonal elements. So the off diagonal elements B21 up to Bj1, and here these elements are nothing but off diagonal elements. Similarly, here you have upper off diagonal elements. So these off diagonal elements are mostly in negative and relatively weaker compared to the diagonal elements. So here the diagonal elements are nothing but B11, B22, and so on up to Bjj. So these are some of the characteristics of this loss coefficient matrix. So we can revise all the summary points one more time. So this loss coefficient matrix is basically a square matrix, and its size is given by the number of generators available in any system. If the system is having n number of generators, then by default the loss coefficient matrix size is n by n. And basically it is a symmetric matrix. That means B is equal to B transpose. And all the diagonal elements are positive in nature and strong when compared to the off diagonal elements. And all the off diagonal elements of this matrix are negative in nature and very weaker compared to the diagonal elements. So now let's see what is the impact of transmission losses on economic dispatch and optimization strategies. So basically, economic dispatch is nothing but allocation of power generation among committed generating units so that the total operating cost is minimized while meeting the load demand and system constants. So mathematically, you can express this statement as the total power generation should be equal to total power demand plus total transmission losses PL, provided the total cost of transmission CT is very, very minimum. So that is what we defined in the previous lectures as economic dispatch. So in the practical power system, you cannot avoid these transmission power losses because every transmission line is offering some resistance. So whenever resistance is there, so definitely you will have some kind of I square or losses, nothing but copper losses. So because of this resistive nature of transmission lines, so all the transmission lines in real time will offer some transmission losses. So you cannot neglect these transmission losses whenever we think about economic dispatch, because our total power generation should also contribute the transmission losses apart from serving the total load demand. So how these transmission losses will affect economic dispatch, that we can see now. If you increase in required generation, so whenever transmission losses are considered, it results in higher generation cost compared to loss neglected ED. So ideally, when you neglect PL, so when PL is equal to 0, so obviously the total cost of generation is quite low, but which is not real in practical power system. So in the practical power system, always you have to consider power transmission loss. So due to which, obviously you have to generate more power. So PG should be more, then which in turn increases the total cost of generation also. So because of this reason only, so whenever you consider the transmission losses, we have to consider one parameter that is called as penalty factor. So this penalty factor will take care of how much excess power is required to meet these transmission losses. And at the same time, whenever you consider penalty factor, the total cost of generation is also quite high compared to the ideal case. So this penalty factor plays an important role when you consider the real power system. So now let's see, the generator location also is very much important because the generator location also show its impact on transmission losses. Suppose let's say if there is one generating plant and the load is located very far away from the generating plant, let's say maybe after some 15 kilometer. After 15 kilometer from the generating plant, if there is a load location, then obviously the entire power has to flow through this long 15-kilometer transmission line. So in the meanwhile, the transmission loss will be there, which is not equal to zero. Suppose if the load is not located here, instead, if the load is connected very near to the generating station, then the distance of power transmission is very, very less. So obviously you will have very less power transmission losses. So that's why it is always required to ensure that whichever is possible, try to minimize the distance between the load demand and also the generation plant. And now, how these transmission losses will show its impact on various optimization strategies. So we have various optimization strategies starting from classical, mathematical and advanced strategies. So in the classical, the best method is lambda iteration method. So this lambda iteration method will become little complex because of introduction of losses. And it requires repeated recalculation of penalty factors and losses because we will have so many cases and we will try to pick any one case where the penalty factor is less and the losses of power is also very less and also the total cost of generation is also very less. So to pick up that best matching case, you have to do repeated calculations. And then if you think about mathematical programming based, the losses can make economic dispatch problem nonlinear and also non-convex. It is not, the power equation itself is not a linear equation. Even if you write the equation for power transmission loss, the PL can be expressed as 3 into I square R. So the reason why I consider 3 is, it is for 3-phase system. So by using this equation itself, we can say the transmission power loss itself is not a linear relation because it is having square term. So it is basically a non-linear relation. So there are some methods like quadratic programming, non-linear programming, NLP. So these programs are very much suitable whenever we deal with transmission losses in case of economic dispatch. So there are some advanced methods by using some meta-heuristic techniques such as genetic algorithms, particle swarm optimization, PSOs, and differential equations D. So they will handle losses very much effectively. They avoid derivative calculations and perform well for large systems. Because when we avoid the derivative calculations, automatically any programming will require very less space. The memory requirement also will reduces. And there are some modern optimization approaches nowadays we are implementing: security constant economic dispatch, multi-objective economic dispatch, and loss minimization integrated economic dispatch. So they consider both cost as well as losses. And now very recently, we are trying to implement some of the AI-based hybrid optimization methods are also. Because AI-based methods can tune to the real-time varying of losses because they are very much suitable for dynamic behavior. So now let's see the mathematical equation that can be used to express transmission losses. So this transmission loss formula can be derived by using the following process. I'll just quickly explain what is the general procedure to be followed in determining this or in derivating this transmission loss formula. So consider a two generating plants system connected to an arbitrary number of loads through a transmission network as shown in figure 1.4. So here we are considering three different cases. In case 1, in the figure 1.4a, there are two generating plants connected to various number of loads here through a transmission network. And in case 1, we are assuming that the entire load demand current is supplied by using only generator 1. So that means the generator 2 is not connected to this network. So that's why the switch is shown in open position here. So consider the entire load current is supplied by using only the generator 1 in case 1, and in case 2, instead of generator 1, consider generator 2 that is supplying the entire load demand current. So that's why now the generator 1 is not connected to network, so the switch is shown in open position. Now consider both the generators are supplying the required load demand current. Both generator 1 is connected to the network and also generator 2 is also connected to the network. So for the three different cases, you can express three different equations here. In the first case, the total load current ID is applied by plant 1 only. So the current that is flowing through this network can be represented as IP1. So now you can express the current density MP1 is equal to IP1 by ID, where IP1 is the current flowing through this network and ID is the demand current. So similarly, let's consider case 2. The plant 2 alone is supplying the total load current as shown in figure 1.4b. So now you can define the corresponding density factor as or distribution factor as MP2 is equal to IP2 by ID. Now where MP1 and IP2 are called as current distribution factors or current density factors. These are called as current distribution factors. Now let's move to the third case where both generator 1 and generator 2 are supplying currents to the load. So in such case, you can express equation as IP, where IP is the current flowing through the transmission network. IP can be expressed as MP1 into I1 plus MP2 into I2, where I1 and I2 are the currents injected at plants 1 and 2 respectively. So let me show this equation symbolically here again. So this is the transmission network and this is the load current ID. We have two generators here. Generator 1 is supplying a current I1 and generator 2 is supplying a current I2, and the transmission network is carrying a current IP. So for this case, the equation can be expressed as IP is equal to MP1 into I1 plus MP2 into I2. So in proceeding, we have to take some assumptions here, because the assumptions can make us derivation simplification little convenient for us. So all the load currents have the same phase angle with respect to the common reference. This is the first assumption. The second assumption is the ratio X by R is same for all network branches. So in general, all the transmission lines will be connected in parallel. So all the transmission lines, whenever are connected in parallel, if you calculate the reactance, you have to take reactance as net equivalent reactance and resistance also as net resistance. So when you calculate the ratio of X by R, it is same for all the network branches. That is the second assumption. So by using two assumptions, now you can say IP1 and ID have the same phase angle. Similarly, IP2 and ID also have the same phase angle, so that the current distribution factors can be made real instead of complex. So the currents are basically AC currents, because whatever the system we considered here is a AC network. So in the AC network, the currents can be expressed in the form of their magnitudes and angles. So let I1 is expressed as I1 magnitude modulus I1 at an angle of sigma 1, and current I2 is expressed as modulus I2 at an angle of sigma 2, where sigma 1 and sigma 2 are the phase angles of I1 and I2 with respect to common difference. So now, once we substitute those equations in the earlier equation, you can express and get this 1.35 equation. If we expand this equation and simplify, definitely here we have cosine terms and sine terms. You are going to have terms like cos square t rho 1 plus sine square rho 1. Similarly, cos square rho 2 plus sine square rho 2. So once you simplify those, you will get the equation as 1.36. It is nothing but IP square is equal to MP1 square into I1 square plus MP2 square into I2 square plus 2 MP1 into MP2 into I1 into I2 cosine of rho 1 minus rho 2. So we know that in the three-phase system, the three-phase power can be expressed as 3 V phase I phase cos pi. This is the general formula that we saw many times in so many courses, where V phase is nothing but phase voltage, I phase is phase current, and pi is the angle between the phase voltage and phase current. The same thing can also be expressed in line values. So when you want to express in line values, it will change to root 3 VL into IL into cos pi. Of course, the relation between phase voltage and line voltage, the relation between phase current and line current depends on the configuration of our three-phase network. So we know fundamentally very well, suppose if it is a delta connected network, we know that V phase is equal to VL and I phase is equal to IL by root 3. Suppose if the network is connected in star manner, then the phase voltage will become VL by root 3 and I phase will become equal to IL. So whatever may be the configuration of network, so fundamentally you can express the three-phase power as 3 V phase I phase cos pi in terms of phase values, or root 3 VL IL cos pi in terms of line values. So by using this fundamental equation, we can express I1 as P1 by root 3 V1 cos pi 1, and I2 can be expressed as P2 by root 3 V2 cos pi 2, where P1 and P2 are the three-phase real powers injected at plants 1 and 2 at power factors of cos pi 1 and cos pi 2. V1, V2 are the bus voltages at the plants 1 and 2. So now we can substitute these I1 and I2 equations here in equation 1.3. Then you can get the equation for power transmission losses. So basically the power transmission loss PL can be expressed as summation P 3 into IP square into RP, where RP is the resistance of the branch P. So now we can substitute that IP equation here in equation 1.38. Then ultimately, if you simplify, we will get the final equation as 1.39. So which consists of three terms. This is the first term, and this is second term, and this is the third term. So once the system design is completed and it is operating at stable condition, so some of the parameters are constants here. So based on that, the same equation 1.39 can be modified as here PL is equal to P1 square into B11 plus 2 P1 P2 B12 plus P2 square into B22, where the terms B11, B12 and B22 are called as loss coefficients or B coefficients. Suppose if voltages are line voltages and resistances are expressed in ohms, then the units of B coefficients are megawatt inverse, and P1, P2 are expressed in megawatt. So this is a very, very important equation. So which can be useful in solving some of the problems, maybe in the current lecture and also in the upcoming lectures. So please try to remember this standardized equation of transmission loss formula. So that is PL is equal to P1 square B11 plus 2 P1 P2 B12 plus P2 square into B22. In general, if the power system is having k number of plants, the same loss formula can be expressed in a generalized form as 1.41, where PL is equal to P1 square B11 plus and so on plus PK square into BKK plus 2 into summation m comma n is equal to 1, where m is not equal to n up to k, PM PMN into PN. So based on this generalized formula, you can write the equation for 2 units, so as we derived in the previous slides. So PL is equal to P1 square B11 plus P2 square B22 plus 2 B12 P1 P2. This is the standard formula for transmission loss. So now, as we see in the previous slides, whenever we consider the transmission losses, one important parameter is coming into the picture, that is nothing but penalty factor. So now let's discuss a little more about the concept of penalty factor, out of which we are going to make some of the important observations. So basically, ELD is the process of allocating generation among committed generating units so that the operating fuel cost is minimized while satisfying total load demand, nothing but PD, and generator capacity limits, because we are not supposed to operate any generator beyond its capacity limit, maximum capacity limit. And also we have to satisfy system operating constants. So as we discussed in the previous lectures, we have 2 kinds of system constants, equality and inequality. So whenever we talk about economic load dispatch, along with losses, the penalty factor will come into picture. At the same time, our total operating fuel cost should be minimized, provided all these 3 conditions need to be satisfied. So in the ideal case, the transmission losses can be neglected. However, in a real power system, the transmission losses cannot be neglected. So obviously you have to consider the transmission losses when you consider real power system. So that will lead to the concept of penalty factor. So when you consider the losses, then only you will need to consider penalty factor. Suppose when you don't consider transmission losses, there is no need to consider about penalty factor. So the transmission losses basically occur because of these 3 reasons. One is due to line resistance, and second one is due to long distance power transfer, and the third one is network topology, in which configuration the network is connected. So that also show its impact on the transmission losses. So basically the losses depends on generator locations, whether the generator is located very near to the load or very far to the load. Suppose if the generator is located very near to the load, then obviously the loss is very less. If the generator is located very far away from the loads, then obviously the length of the transmission line required is more, then the transmission loss also will increase. The power output, the loss also depends on the power output levels of generators and the system configuration. So the total power generated may not be equal to the power delivered to the load because of these transmission losses. So that is the reason. So we can express as the total power generation is equal to total power demand plus total power transmission losses. So this particular equation is called as power balance equation. As we see in the previous lectures also, this PG is equal to PD plus PL is called as power balance equation, where PG is total generated power, PD is total demand power and PL is total transmission losses. So now let's see what is the need for considering this penalty factor. Suppose let's say if losses are neglected, then a generator with low fuel cost but high losses may be selected. So whenever we neglect losses, we don't think about the losses, we think about only the fuel cost. And obviously we are going to select, suppose if there are n number of generators, out of n number of generators, the generator which is having low fuel cost can be selected for higher generation. And if the losses are ignored, the total system cost may also increase. To account losses without reformulating entire optimization problem, the penalty factor can be taken as a useful parameter. So whenever you consider this penalty factor, it is going to modify the equation also, and it is going to modify the incremental fuel cost of the each and every generator. So it converts local generation cost into effective delivered cost, because when you consider the losses, that is with respect to the delivery. After transmitting power over a long distance through a long transmission network, the power can be delivered. So that involves some cost with respect to the power transmission loss also. So based on all these concepts, you can define this penalty factor for ith generator as Li is equal to 1 by 1 minus dou PL by dou PI, where this Li is called penalty factor of ith generator, that can be expressed as 1 by 1 minus ITL, where ITL is expanded as incremental transmission losses. This ITL is called as incremental transmission loss. And this can be expressed mathematically as dou PL by dou PI for ith generator. So basically, this penalty factor represents the ratio of incremental generation required at the generator to incremental load losses of the load bus. If you don't consider the penalty factor, then the condition for economic load dispatch is given by dCi by dPi is equal to lambda. When we try to expand this equation, we can write this as dC1 by dP1, that is equal to dC2 by dP2, and so on up to dCn by dPn is equal to lambda. So where dC1 by dP1 is called as incremental fuel cost of unit 1, dC2 by dP2 is termed as incremental fuel cost of unit 2, and so on. That is equal to lambda, where lambda is called as Lagrange multiplier. So this particular lambda is called as Lagrange multiplier. So we can say this condition in terms of words as, when we neglect the transmission losses, the condition for economic load dispatch is as the incremental fuel cost of all the individual units should be same and should be equal to Lagrange multiplier lambda. Now, when it comes to the real case, the real power system, we have to consider the losses. Then the condition for economic load dispatch is given as dCi by dPi into Li is equal to lambda. So this particular equation can be expanded as dC1 by dP1 into L1 is equal to dC2 by dP2 into L2, and so on up to equal to lambda. So in terms of watts, we can call this condition as, when we consider the transmission losses, the condition for economic load dispatch is stated as the product of individual units incremental fuel cost and its penalty factor should be same for all the units, and that should be equal to lambda. So this particular equation ensures that minimum total cost including transmission losses. So now some of the observations we can make out of the definitions of penalty factor. So in general, the penalty factor is either equal to 1 or greater than 1. Suppose if penalty factor PF is equal to 1, that means generator at load center. The generator is located near to very load center. Then there is no requirement of transmitting power over a long distance. Suppose if the penalty factor is very high, that represents generator is electrically distant. That means the generator is connected very far from the load center. Generators with lower penalty factor are more economical. Suppose if there are two generators having two different penalty factors, we obviously choose the generator which is having lowest penalty factor. A generator may have low fuel cost but high penalty factor. This case cannot be preferred one. You can understand this by using this example. Suppose if dou PL by dou PI is equal to 0.1, if you substitute this value in penalty factor equation, then you will get penalty factor as 1.11. So which will indicate as to deliver 1 megawatt of power, the generator must produce 1.11 megawatt of power. That means the additional 0.11 megawatt of power is required to meet the transmission losses. So whatever the concepts we have seen so far in this lecture, let's try to incorporate in solving one example numerical problem. So this is the example numerical problem by which you can understand the importance of penalty factor. A two-bus system is shown in figure here. If 100 megawatt of power is transmitted from plant 1 to the load, a transmission loss of 10 megawatt is incurred. Find the required generation for each plant and the power received by the load when the system lambda is rupees 25 per megawatt hour. Here the power system diagram is given, single line diagram is given. There are two power plants as you see in the figure. PG1 is the power output of plant 1 and PG2 is the power output of plant 2, and the load is connected near to the plant 2 and there is no load connected near to the plant 1. So the two generators incremental fuel cost equations are given here. DC1 by dPg1 is the incremental fuel cost of plant 1 and DC2 by dPg2 is the incremental fuel cost of plant 2. So here the load is connected at only load 2. So for this case, you have to find the required generation for each plant. That means we have to find PG1, PG2, and also we have to find what is the power transmission losses, and then we have to find what is the power delivered to the load. So let's see the solution now. As you can observe here in the given figure, the complete load is connected at only plant 2 and it is not available at plant 1. So then the power produced by plant 2 will not have any effect on transmission losses PL. So that means the loss coefficients which involve plant 2, that is nothing but B22 and B12 will become 0. And we also saw that Bij is equal to Bji. That means you can express B12 also as B21. Of course, it involves plant 2, so by default, its value will become equal to 0. So fundamentally, we have transmission loss equation as PL is equal to B11 P1 square plus B22 P2 square plus 2B12 P1 P2. So once we substitute B22 and B12 as 0 in this equation, then this particular transmission line equation will be turned as PL is equal to B11 into P1 square. So since PD1 is equal to 0, because there is no load connected at plant 1, so that's the reason we are taking PD1. The load demanded at plant 1 is equal to 0. So then PG1 itself is equal to P1. And in the problem statement, it is given as if 100 megawatt of power is transmitted from plant 1 to the load, then a loss of 10 megawatt of power will be lost. 10 megawatt of power will be lost. So using that statement and using this PL equation, you can determine the loss coefficients. So here PL is nothing but 10 and power generation is 100. So by using that, you can get B11 is equal to 0.001 per megawatt inverse. So now for the plant 1, you can express the condition for economic load dispatch as DC1 by DP1 is equal to lambda into penalty factor 1 by Li. DC1 by DP1 is equal to lambda into 1 by L1. So where 1 by L1 can be expressed as 1 minus dou PL by dou PG1. So dou PL by dou PG1 you can get from this equation. If you differentiate that with respect to PG1, then it becomes lambda into 1 minus 2B11 into PG1. And similarly for plant 2, you will get 0.04 PG2 plus 20. This is nothing but DC2 by dPg2, incremental fuel cost of plant 2. That is equal to lambda into 1 by its penalty factor L2. So 1 by L2 can be expressed as 1 minus dou PL by dou PG2. So we have PL equation as B11 PG1 square. If you differentiate this equation with respect to Pg2, it will become equal to 0. Then that particular equation will become equal to lambda. So by using these two equations and substituting the value of P11, you will get the values for Pg1 and Pg2 as Pg1 as 128.57 megawatt and Pg2 as 125 megawatt. So now you can, once you get the value of Pg1, you can determine the value for transmission loss using this equation B11 into P1 square. Then if you simplify, you will get the transmission loss of 16.53 megawatt. So now consider the power balance equation. What is the power balance equation? The total power generation. There are two generating units. So the total power generation will become equal to Pg1 plus Pg2. That should be equal to the total power demand plus the total power transmission losses. So from this equation, we can write Pg2 is equal to Pg1 plus Pg2 minus Pn. So once we substitute all the values here, then you can determine the value for power demand as 237.04 megawatt. So the important observation by solving this numerical problem is whenever you want to incorporate the losses into real time, then you have to take care of penalty factor. You have to consider the penalty factor. Using that only you can determine all the scheduling powers for each and every power plants. So the summary of today's lecture is we saw the loss coefficients and the properties or characteristics of loss coefficients, and we have derivated the transmission loss formula, and then we expressed transmission loss by using a general expression, and we discussed about what is the effect of transmission losses on economic dispatch, and we discussed about concept of penalty factor and what is the need for penalty factor, and we have defined the penalty factor and what is its role in economic load dispatch. We have seen by solving one example problem. So that's it for now lecture. Thank you all. We'll meet in next lecture.